do we get when we line up all the numbers in order from smallest to largest and select the one in the middle? So type in your answer to question 1. I'm going to put numbers on these so we're speaking the same language. Question 1, please type your answer in. When I get about 5 answers, we'll move on. Thanks, Stephanie. Rufina, excellent. Sean, very good. 2 more. Yes, Cheryl and Colin, excellent. This is the median. It's the number that's in the middle of a distribution. Number 2, what measure of central tendency do we get when we sum all the values and divide by the total? I'm going to change this to number, and I'm going to write N, because that's how we'll be abbreviating this later on. Correct, Sean. Looking for 4 more answers to number 2. We sum up all the scores. This is why we have to be careful with our language. All right. Shannon, Rufina, thank you. Let's see if I missed anyone. Sherilyn. Okay, Tiana, very good. That is the mean. That's the number we're going to use most in this class. This is mean, and we'll write M because that'll be our abbreviation. And what measure, number 3, what measure of central tendency should we use if we have a skewed distribution? A skewed distribution. We talked about mean, median, and mode, which is going to be best if the distribution is skewed. Okay, Shannon, correct. Stephanie, yes. Lyle, excellent. Sean, Tiana, good. You guys are right on top of your game. You said you should use median, and you're correct, because remember that outlier works like a magnet, pulling the mean off center. So don't use it. And I already introduced you or reminded you that we're going to, for what we're doing now, we're going to be using the letter M to indicate mean. I took the last question off because I haven't introduced it yet and we don't need it yet. So, so far we've learned to explore the center of a distribution through mean, median, and mode. We've learned how to explore the shape of the distribution. We learned that in chapter 1. Today, we're going to learn how to quantify, that is, put numbers to the spread of a distribution, or how far the scores are from the center. And I'm going to put it into play mode here, but probably I'll have to pull it out because my pen won't work. So we already know that in a normal distribution, mean, median, and mode are equal. We know that in a skewed distribution, the mean is pulled toward the tail. You can see, yeah, my pen's not going to work in here, so let's just continue on. So here's some terms that we're going to be just reviewing here. So when we say this word distribution, all we mean is the collection of scores on a variable. And so we're looking at how are those scores distributed, and we call that the distribution. We remind ourselves that the values are the scores on the x-axis, and the frequencies are the scores on the y-axis. And the variable is that trait or characteristic that we're talking about. Now, in this slide, we see a beautiful normal distribution, and it's a perfect one. And it's like what we call a prototype. It's like an example of what it would be in a perfect world. But we do not have a perfect world, but this is what it looks like, the perfect bell curve. But more typically, we have distributions that look like these. And there's nothing wrong with any of these distributions. All of these would still be considered normal. So if you were asked what is the shape of any of these distributions, you could feel comfortable saying it's normal. It's normal. It's normal. And we're going to look at why through this little pinko probability game here. I don't know why it's named as it is, but that's what it's named. And what we're going to do is we're just going to look at how distributions play out. And the way you can conceptualize this is think about if you're rolling pairs of dice. On your very first roll, it's possible you'll get a 12, right? And on your second roll, maybe you're going to get a 12 again. You know, all of that is possible. But what happens if you roll like 1,000 times that pair of dice? That's when you're likely to get the normal distribution. And in fact, it's likely to be pretty normal with as few as 30. So let's take a look at, let's just roll these a few at a time. So let's just drop one ball in here and see where it goes. Okay, there it is. Let's put another one in. Where's it going to go? There we go. So nothing's looking normal yet. Let's do a couple more. We don't have any that jumped way off to the side yet. They're kind of spread out here around the center. Let's try a group of 10. Okay, still doesn't look normal. So far we have 15 in our sample, but we do have more toward the center and we have fewer off in the tail. So we actually have the start of a normal distribution. Let's see what happens with another 10. Okay, it looks a little kind of skewed here. Still, we do have more values toward the center, and let's see what happens with another 10. Every time it's different. So this is what random means. Every time is going to be different. Ooh, we have a nicer pile up in the middle, but we still have a little bit of a skewed looking distribution. And we're at 35. Let's see what happens if we take it up to 50. Ooh, we're starting to look a little more in the center, and let's do 5 more to take us exactly to 50. Okay, and so this distribution now, I think we would say it's not perfect normal, but if we were just for the sake of statistics trying to define the shape of this, we'd say it's normal. And so let's do one more example. Let's imagine now that all of these balls are drawn from a population and they're just randomly selected ages of people in the population. And so the first random group of people we pulled, that's what we got. Now let's go ahead and refresh it and draw another random sample of people. We'll draw 30 people. So here's 10. We'll let these 10 come. These are the first 10 people, nice flat line almost. Let's try another 10. These are the ages, we just drew them at random. This is what we got. And let's draw 10 more. All right, and so let's go up to 50 actually, like we did last time, for the sake of comparison. And one more. Okay, so once again, it's sort of approximately normal, we might say. So some terms we'll be working with later. These balls, in this case representing individuals from the population, these would be considered our sample. And the big bucket of balls, or all the people in the world, would be our population. Okay, and so we assume that this sample represents the population, and we consider that it would be normally distributed if we got enough drawn out of it. But we know that the ball, if we drew like hundreds and hundreds, we knew it would be normally distributed. And just to play this out a little bit more, Let's just play this through a little more. Doesn't look great now, but if we keep drawing from the population, it gets increasingly normal. Not perfectly normal, but it takes on more of a normal shape. And if we went on indefinitely, which this doesn't have the capacity to do, it's not big enough, we would see that it would get increasingly normal over draws. So this is an important concept we'll talk about more, but I wanted you to just think about this in the first place. The distributions we get aren't going to be perfectly normal, but they likely represent population that would be normal if we had enough. So continuing on then, let's give a little more thought to this. So even in normal distributions, even if we have two normal distributions, some differences can exist. So first off, let's look at this distribution. It's kind of tall and skinny. I don't know if I'd say it's exactly kurtotic because I don't really see the heavy tails, but we do have a thin distribution. And let's imagine that these are representing housing prices. So the least expensive houses are down on this lower end, and the most expensive houses are on the upper end. And we see that in the middle here is the mean. And so let's imagine, say you're in Phoenix or something, and you're in one of those suburban neighborhoods where all the houses are kind of, you know, they're all like similar in value or something like that. Or if you're at something like Dene College with those places that I'm living in, they're all kind of similar. You know, they're not very different from each other, those hogons. And so you'd say maybe the mean housing price is in the middle here, and there's a few on either end, but there's not much variability. The neighborhood is really consistent. And now let's picture this second neighborhood. And this is a neighborhood where the housing is really diverse. Like in Madison, Wisconsin, a place I'm familiar with from younger years, there was actually a law that every neighborhood had to be diverse. Like you couldn't have a neighborhood that was just rich people or just poor people. You had to have some houses for people who didn't have much money, and some houses for people who had a lot of money, and more houses that were in the middle for people who had average amounts of money. And so you can see these are two neighborhoods. Now let's imagine that the mean or the average is the same in both groups. Let's imagine that the mean in this case is 150,000. And the mean in this case is 150,000. The means are the same, but these distributions are very different, aren't they? We have a lot more diversity in this lower neighborhood. And so this is the aspect of a distribution that we're looking at today. We've looked at center when we talked about mean, median, and mode. We looked at shape when we talked about normal, skewed. And now we're looking at spread. So how far apart are the scores from this mean? And that's the concept that we're working with today. And so there's some, this is the image that we're going to be working with. How broad is the distribution? We can see this center, we have a narrow distribution in the red. And in this green, we have a broad distribution. And here in the center, we have just this normal kind of typical average distribution. But these all could be considered normal, but the spread is going to differ. So I have a question for you. I'm going to be introducing to you two terms today in kind of like metaphorical ways so that you really understand the terms. And I'm going to start by talking about deviation. Deviation. So when we say deviance or deviation, what do we mean when we use it in our common language? And someone, for example, might say, Trevor was engaging in deviant behavior. You might hear people in a school say this. So if someone made this statement, what would they mean? What would they be saying about Trevor's behavior? Colin, happy to see you. Do you have any thoughts on this? Someone's engaging in deviant behavior. Anyone who has thoughts could speak up, but I want to engage with you just a little bit on this idea.
Is it a standalone?
This person kind of stands out. Absolutely, yeah. So the person is deviant. Can anyone add more to it about the nature of what we mean, what we might mean when we say deviant behavior?
Opposite?
Okay, opposite, different, could be
Different? Yeah.
opposite. Opposite to what?
Opposite to a group? Or
Opposite to the group. All right, so differently from the group. Okay, good. Has anyone ever, if we use this in a school, like what kinds of things might Trevor be doing, do you think?
Dr. Russ?
Yes.
It usually means deviant behavior would mean negative behavior.
Often it means negative, yeah. But it's deviant from, how would you say deviant from what, Sean? And what exactly might Trevor be doing?
Deviant would probably mean in like a school setting, what the norm would be.
What the norm would be.
Yeah.
And so can you give an example of what the norm might be and what Trevor might be doing that would be deviant?
Well, let's say there's a dress code of the school, and that individual might be wearing something that is not the norm, which would be something, let's say they outlawed rock and roll t-shirts or something, and he comes in with something that's very graphic. So right now, a counselor or teacher would say, so-and-so is displaying deviant behavior. Get him in here as soon as possible, call his parents or something like that.
Yeah, I actually really love your example, and I'll interrupt this with a sort of a funny story. And you'll notice right now, my shoulders are showing, and I tend to, in summer weather, I'm comfortable that way. But this summer I went to visit my son in Korea and meet my granddaughter. And so in Korea, oh, women don't wear their shoulders out like this. Oh, no, no, no. Even young women, they wear like a really light something or other that covers their arm, almost their whole arms, but certainly their upper arms and shoulders. And so when I got to Korea, I knew this from an earlier time, but I had forgotten how serious this was. And so I felt like I was engaging in deviant behavior if I had my shoulders out. So I took great care to like find blousy things to put over my shoulders because I did not want to be deviant. I didn't want to be different from the norm. So that's what we mean, different. I like that you use the word norm. So whatever's normal, expected. And that's what we mean. And I have a version of that here. We're using that word norm, Sean. Behavior that differs from the norms upheld by a majority of people in a given situation. So I just copied that down from a definition in sociology, okay? But I want you to keep this idea, because when we talk about deviation in statistics, we mean the same thing. So I want you to become comfortable with our language. So in statistics, we say it's the measure of a difference between the observed value and some other value. So that might seem confusing, but note this common word. I have to exit out here in order to write. Note this common word difference. This is what we're talking about. Difference from a norm. And in statistics, we're also talking about difference from a norm. And what's the norm in the case of a distribution? The norm is the mean. So the norm is telling us where are most of these numbers hanging around. They're hanging around the mean. And the deviation is how far is an individual score from that mean. And so looking at this distribution, this is our population. And let's imagine that in this case, the mean is right here where the median is. Let's say it's about here, it's 10, or maybe it's a little around 10, but let's imagine that in this distribution, the mean equals 10. So what are our deviations? Well, the deviation would exist for each score. So if this is the mean, then we figure out how far is this score from the mean, and this score, and this score, and this score. How far away are they? So with my little shoulder violation, potential shoulder violation in Korea, that probably would be kind of maybe, well, I know how to characterize that. If we think of societal norms, it was probably a minor deviation, but there might be much more major deviations that might be way far from the mean, like if we started to engage in, say, violent behavior or vandalism or something like that. So that's the deviation. How far is each score from the mean? So if the mean equals 10, then each deviation, DEV I'll abbreviate, would equal X referring to each score, minus M. That's what a score's deviation is. It's just each score minus the mean. So in this case, this 14, so for this score right here, this is, let's call this X1. So the deviation for X1, so we'll put deviation, and in parentheses, I'll put X1. I should have put the 1 down here. And I'll put equals 14 minus 10 equals 4. So the deviation for X1 is 4. The deviation, let's say this one right here, let's name it X2. The deviation for X2 equals 11 minus 10 equals 1. I wonder, can anyone find out what the deviation would be for X3? If you can figure it out, plug it into the chat box. Working with negative numbers a minute here. The deviation for X3. All right, very good. And I'm seeing 2s and negative 2s. And so let's take a moment to work through this. In some ways, you're both right. It's X minus M, so it's going to be 8 minus 10, which is in fact negative 2. Okay. If you are straight up going to use the absolute value, how far apart is it from the mean? We would want to say 2. Because we're working with these numbers, we're going to always put that negative in there, but in the end, it's not going to matter. So yeah, negative 2 is technically the answer, but conceptually 2 is the answer. So that's the idea of a deviation, and we're going to be working with that. So the next term we have to work with is standard. And when we talk about standards, we're talking about the accepted or approved instance or example of a quantity or quality against which others are judged or measured or compared. So I imagine those of you with children, you have some standards of behavior for your children. You have a norm that you expect them to reach. If they don't meet that norm, maybe they're deviating from that norm. Okay. But we have standard units that we work with too. And so when we're talking about standards in the case we're mostly using in statistics, it's the same idea, but it's just like a common language. Okay. So we have a standard unit of dimension in the US is inches. We have pounds as a standard weight, minutes, second, hours as a standard unit of time, quarts, ounces as a standard unit of volume. Well, what we're thinking about here then is something we're going to take this concept, we're going to work with it today, and then again on Tuesday with a new idea. But first, let's just think about this idea of a standard unit of measurement. And I'll add that, by the way, when I was a child, maybe I know some of you might be my age more, the inches that we use as the standard unit of measurement in the US, we use inches, pounds, and quarts. Well, way back when I was a kid, the rest of the world moved over to the decimal system. That is liters and kilograms and centimeters. And there was a lot of, we started to learn all that because we thought we were going to change. And then we decided we were, as a US country, we were going to deviate from the norm set by the world, and we weren't going to do it. So now we have these two standards of measurement because we decided, no, we're not going along with this sensible measurement thing. So we stood solid and stayed with our old measures for whatever reason. And I'm going to skip through my next two slides and just jump right into the math, and we'll visit those next time. So when we think about a standard deviation, what we mean is the measure of spread in a particular distribution. So if this is our particular distribution, this distribution standard deviation telling us about how far scores are from the mean. So how far on average are scores from the mean? So we might say it's like the distance that a typical score in this distribution deviates from the mean. And we already looked at how we can have a small standard deviation, like here, if we have a really narrow set of values. Or we could have a large standard deviation, like here. And so it's just the number of distance of how far scores are from the mean. We already showed these homes. Okay, so we're just going to look at some calculations of how we figure this out and what it means. So really quickly, let's work with some ideas of deviation before we put the standard in. So here we have a distribution of test scores. The distribution of test scores in Tara's class has a mean of 78. Tara got a score of 88. So Tara is, we're going to figure out the deviation for Tara, and Tara is going to be score 1. And in this case, the deviation for Tara, who is x1, equals, as you know, x minus m. And what would this equal? And let me look for 5 answers in the box, please. What is Tara's deviation score? Yes, Shannon. Very good, Sean. Tara's deviation score. Formula simply x minus m. We can see x and we can see m. Thanks, Rafina. Lyle, yes. One more. Yeah, we know that it is simply x, which is 88, minus m, which is 78, and so it equals 10. Skipping down to number 3, the average high temperature in July is 85 degrees. So the distribution that we're looking at is actually all the Julys across year. But the average in July 2021 was 88 degrees. So if we averaged up the scores for all the Julys across time and averaged up the temperatures, it's 85 degrees. So all the days in July and all the Julys in history is 85 degrees. But 2021, the average was 88 degrees. How much did July 2021 deviate from the mean? Yeah. Sherilyn, great. Sean. Stephanie, terrific. Shannon. Okay, one more. Oh, you guys, when you post these up, put them in private if you want so that everyone has to think of the answer themselves. Yeah, simple, right? We just take, in this case, X is 88. July 2021 is 88. So deviation. And maybe I'll put here, this is going to be for July 2021 equals X minus M equals 88 minus 85 equals 3. All right. So in order to figure out what this means for the distribution as a whole, we do a little bit more math. So don't worry about all this just now, but remember I told you that the standard deviation, or SD, is, is sort of like the average, deviation. But we do a little bit more that we're going to do time and again in statistics so that the formula isn't quite as easy as we want it to be. If it was the average deviation, it would look like this. Equals, we know what an average is. We would take the sum of all the deviations. Don't write this down because this isn't going to be right. And we divide by n. And that would give us an average deviation. But we're going to make it a little more complicated than that because we're going to add 2 steps to it. The first thing we're going to do is, instead of taking the sum of all the deviations and leaving it there, we're going to take the sum of all the deviations squared. So we're going to take all those deviations and we're going to square each one of them. And then we're going to divide by n. And then for our last step, because we squared all those things, we have to take the square root of that figure that we get. So this is the formula for standard deviation that we'll be using at this time. So to go over that again, the steps we're going to follow are these. First, we're going to calculate the deviation for each score. How far is each score from the mean? We've just done this. Next, we're going to square each deviation. Then we're going to sum up these deviations to get what we call the sum of squares. So the sum of squares we're going to work with a lot. It's the sum of all those deviations squared. Each deviation squared, and that's called the sum of squares. Then we're going to divide by n, this step we looked at here, and we're going to get something we call the variance. And the variance is just sum of squares divided by n. That's our variance. And then we take the square root of that. For our standard deviation equals the square root of the variance. Those are the steps we're going to follow, and this is the formula in its complete form. But we're going to be using these steps, and so let's do an example now. So guided practice, this is just what we're going to do in class here. So we can see our scores, and I'm going to make this really small. This is an example of what a problem might be. We're actually going to skip a little piece of this here. All we're going to do is find the mean and standard deviation, and then we're going to explain it. Okay, if we can. We're going to find the mean and standard deviation. There we go. So let's go ahead and lay out these scores. Let's organize our data in a nice readable raw form. If you have had math classes in the past, they might organize a problem like this a little differently. I'm going to encourage you to use this table form to organize your data, because this is how we're going to be doing it in Excel, so this will help you. So what I want to do is first write down the scores. And so if I looked at the data, what we would actually have here I'm going to take this heading off here and move this problem up so that I can. Oops, so that I have a little more room to write. So here we go. So we have for the raw data, we would have, first of all, we would have game 1. I'm going to put G1, G2, G3, G4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to game 10. And then if we organize the scores, we're going to have, I'll put a heading here that says X, and we'll have 0, 3, 6, 8, 2, 9, 7, 6, 4, and 5. And next we have to calculate our deviations. So our deviations, remember, is X minus M. And so in order to calculate X minus M, we have to calculate M. Remember what M is. M is the sum of all the scores divided by N. And so M equals the sum of all of these values. So I'm going to add them up. 5 and 4 is 9, and 6 is 15, and 7 is 22, and 9 is 31, 33, 41, 47, 50. Divided by 10 equals 5. So in this case, the mean of this distribution is 5. So let's figure out each deviation. The first score is 0, X minus M, 0 minus 5 equals negative 5. 3 minus 5 equals negative 2. 6 minus 5 equals 1. 8 minus 5 equals 3. 2 minus 5 equals negative 3. 9 minus 5 equals 4. 7 minus 5 equals 2. 6 minus 5 equals 1. 4 minus 5 equals negative 1. And 5 minus 5 equals 0. So now we have the deviations. Next, we need to figure out for each score the deviation squared. Deviation squared, or X minus M squared. We've already figured out X minus M, so all we have to do is square it. So negative 5 times negative 5 equals 25. Negative 2, I'll just put this dot, times negative 2 equals 4. 1 times 1 equals 1. 3 times 3 equals 9. Negative 3 times negative 3 equals 9. 4 times 4 equals 16. 2 times 2 equals 4. 1 times 1 equals 1. Negative 1 times negative 1 equals 1. 0 times 0 equals 0. And so these are our deviations squared. Our next step is to sum all those squared deviations up. So we're going to put SS, which means sum of squares. And down here, I'm going to write SS equals sum of squared deviations. Or we usually just say the sum of squares. So that just means the sum of deviations squared or the sum of x minus m squared. Notice that x minus m and deviation are the same. So we sum our squared deviations. We have to just add all these up. So I'm going to start with 16 and 4 is 20, 21, 22, 31, 40, 41, 45 plus 25. 45 plus 25 is 70. So our sum of squares is 70. Next, I think I'm going to get a different pen so this isn't so filled up with red. Next, we calculate what we call our variance. Sorry, I didn't get my pen I was going for. Our variance is just sum of squares divided by n equals 70 divided by 10 equals 7. VAR equals variance. And the variance is a strange number that doesn't make a lot of intuitive sense, but we use it all the time when we're calculating. So it's important to understand the idea of variance. And lastly, we're almost done. We simply have to get our standard deviation. Our standard deviation equals the square root of the variance, equals the square root of 7. And for that, we need to use a calculator. So here is my calculator. Sorry if that screen got lost a moment. I think you still see it now. And so the square root, we're just going to write, I believe this way. I don't use my calculator much. So I'm going to hit 7 and put the square root sign, I think. And I get 2.6457513, et cetera, et cetera. We don't need to write all of this down. We can just, usually 4 digits is the standard. If you're in the middle of a formula, and then if you're presenting your results, you usually stick with 2 digits. Since we're doing the math, we'll err on the side of caution and use all 4. So I'm going to take the 7 at the end. It's followed by a 5, so I round up. So I'm going to round it to an 8 and write standard deviation equals 2.54. Let me see, what was that last number again? 6458. 6458. And so now we finish this problem. The answer to this problem would be m equals 5, standard deviation equals 2.6458. And that means, if you were going to explain it, that on average, this basketball player scored varied from the mean, the number of points scored by this basketball player varied from the mean by a little over 2.5 points. So if I was going to write an answer that involved writing the answer and explaining it, my answer might look something like this. M equals 5. Standard deviation equals 2.6458. And then I would write, explaining this to a 6th grader, What that means is you're explaining it in words that would be easy to understand by anyone. So I would say, on average, this player scored 5 points per game, but the points he scored in any individual game differed from the mean by approximately 2. I'm going to write and a half just to keep using words, approximately 2.5 points. And I think that would be good. I think that would be acceptable. Questions about what we've done with standard deviation. And remember, any questions you have are good ones. So I'd love to have some questions right now before we do another example and begin to start our application problems. Virgie, hi. I am there in person next week. I hope you'll come back. Please come back. Stephanie said she's coming back. Sherilyn's coming. I hope Colin's coming. What questions do we have? Stephanie, how is this seeming to you? Does this make sense to you? This is time consuming. That's why we're going to do this next problem.
Yeah, it